Hey everybody, this is the first video lesson in the Unit 15 on nuclear chemistry. If you'd like to follow along in your textbook, this is covering material from Chapter 21. Now the first thing we're going to talk about is the nuclear stability of an isotope of any particular element, and we'll also touch on radioactive decay. Now before we do that, we need to establish something called a nuclide notation. A nuclide notation shows only the nucleus of an isotope, and the numbers in the upper left-hand corner and the lower left-hand corner represent the mass number in the top left and the atomic number in the bottom left. And the way you remember this is that the mass number is always bigger than the atomic number, so the mass number is going to go up high and the atomic number is going to go down low. We identify the mass number as A, and we identify the atomic number as Z. Now, obviously, the symbol is going to be matching the atomic number because you can't have lithium without an atomic number of 3, just like you can't have oxygen without an atomic number of 8. But the mass is going to be changing, and the different masses are going to identify the different isotopes of a particular element. Now, sometimes those isotopes are stable, which means that they will not spontaneously break down through radioactive decay, but sometimes they are unstable. And the instability of an isotope depends on how many neutrons there are. And so when the mass changes, it may result in an unstable nuclide, or an unstable nucleus. An unstable nucleus will undergo decomposition to form a different nucleus that is more stable. This is done so spontaneously. Now, I know we talked about spontaneity in terms of Gibbs free energy in previous units, but in the world of nuclear chemistry, the rules of regular chemistry or chemical reaction chemistry do not really apply. Nuclear chemistry kind of stands alone as a study of chemistry that's not the same. So any of those rules may apply that we learned about, such as the law of conservation of mass and the law of conservation of energy, but any of those laws that we talked about previously may or may not apply to nuclear chemistry. So if a nucleus is unstable, it will decompose spontaneously, and it has a couple of different options in how it does that. Sometimes it actually decomposes, sometimes it just transforms, which we will talk about in the next couple of slides. But a nuclide is a nucleus with a specific number of protons and neutrons, as we talked about already, and I showed you what a nuclide notation really was. Now, what we found or observed is that nuclides with 84 or more protons are unstable, always, regardless of how many neutrons it has in it. And so bismuth is kind of the last stable nucleus of the periodic table, and anything larger than bismuth, which is atomic number 83, is going to be spontaneously radioactive no matter what. And we'll talk more about how and why that happens here in a little bit. We've also noticed that when it comes to stable nuclei, when the protons and the neutrons are equal to each other, or in other words, the neutron to proton ratio is equal to 1, then these tend to have stable nuclei. But if that number is not true, then it's an unstable nucleus and likely going to radioactively decay in one form or another. Now, for heavier elements, when the atomic number exceeds 20, so after calcium, then the neutron to proton ratio does not necessarily equal 1 to 1. And actually, you start to get more neutrons per proton in these higher elements. For example, like iron has 26 protons, and the most stable nucleus of iron would have 30 neutrons. And so it's not quite a 1-to-1 ratio. And it actually gets further away from a 1-to-1 ratio the heavier you get. So essentially, what you need to know is that as the elements get bigger and you pack more protons into the nucleus, we need more neutrons to kind of keep the positive protons from interfering with one another and causing the nucleus to just decay spontaneously. I put a little note here on the bottom about the spontaneity, but we already talked about how any non-stable or unstable nucleus is going to spontaneously decompose. Now, the amount of time that it takes to spontaneously decompose is definitely different depending on the substance, but the point is that they do spontaneously decompose. But we'll talk about the time it takes to decompose in what is known as half-life, a concept that will carry over from chemistry and kinetics, but still applies here for nuclear chemistry. A quick note on a couple of trends that we notice when it comes to elements and their isotopes and nuclear stability. Certain combinations of protons and neutrons seem to confer special stability. Typically, even numbers of protons and neutrons are often more stable than those with odd numbers, and certain numbers of protons and neutrons produce especially stable nuclides. They are called magic numbers. So if you have this many number of protons or this many number of neutrons, or if you add the protons and neutrons together and you have a number like 2 or 8 or 20 or 28, then these are typically referred to as the magic numbers. So these can apply to just the number of protons, these could apply to just the number of neutrons, or these could apply to the mass of an isotope. And they happen to be, or are typically, stable. So in our notes here, I've got a couple of examples where I want you to predict if these are especially stable and explain why. And sometimes we write the isotopes with their mass, but I've rewritten them in their nuclide notation, so it's easier to identify the number of protons and the number of neutrons. And so we've got helium, calcium, and technetium. Now this first one, helium, is stable because it's got an even number of protons and an even number of neutrons, and that proton to neutron ratio is 1:1 as long as the atomic number is less than 20. So helium is stable. Second, calcium, once again, 20 protons, even number. 40 minus 20 is 20 neutrons, even number. So we've got the even number combination that we talked about on the last slide. And calcium is that last element where we see a 1:1 proton to neutron ratio. That means that it's stable. And so both of these first two are stable. Now technetium has 43 protons, which is an odd number. So that's not good for technetium because even numbers are preferred for stability over odd numbers. And if you take 98 minus 43, you get 55, which is another odd number. So we've got an odd number of protons, an odd number of neutrons, and none of these numbers are magic numbers. 98's an even number, but it's not one of the magic numbers. And so because of the fact that it's got an odd number of protons, odd number of neutrons, and non-magic numbers, then this one is going to be unstable. Now we're going to talk about the types of radioactive decay or radioactive transformations that an unstable nucleus may undergo. Now the first one I want to talk about is called alpha production, or also known as alpha decay. This typically happens when you have a really, really big element like uranium-238, and what happens is it's so unstable that it breaks down into a lighter element, thorium, and it releases a helium nucleus. This is what is known as an alpha particle. That's why it's called alpha decay. The helium nucleus is always produced in an alpha decay situation. Alpha production typically is reserved for elements that are much, much bigger than that bismuth number, which I talked about before. But other elements that are smaller may go through alpha decay, but you see this most typically in those really big elements. The advantage of alpha decay is that you can reduce the number of neutrons and protons from the original parent isotope. This uranium is what's known as the parent isotope, and these two are known as the daughter isotopes. And so alpha production can drop 2 protons and 2 neutrons at a time when it releases this alpha particle. Now, along with the alpha particle, oftentimes, along with that, you get some radiation released in the form of electromagnetic radiation. Typically, gamma radiation is the most dangerous, and that is the stuff that can really mess you up. It can rip through your cells and your DNA and scramble things up, and this is how you can be affected by radiation poisoning, by being exposed to high energy photons of electromagnetic radiation. Now, the next one we want to talk about is a beta production. And beta production is not necessarily something that loses mass, because as you can see in this example, iodine is 131, and the xenon, the daughter isotope, is also 131. So in beta production, mass is not lost, but one of the neutrons gets converted to a proton, and as a result, the electron is also produced. It's ejected out of the nuclear reaction. And so something like iodine can turn its odd number of protons to an even number of protons. Remember, even numbers are preferred for stability. But in order to do that, it needs to fire off a high velocity electron, which is then what we call a beta particle. So in beta production, a neutron in the nucleus of an unstable nucleus is converted to a proton, and an electron is formed. Now in these next two examples, they're actually going to take protons and turn them into neutrons, and they can do it in one of two ways. The first one is a little bit more rare, but does happen, and it's called a positron production. So what it does is take a proton and turn it into a neutron and a positron. Now what is a positron? A positron is basically an anti-electron. An electron has no mass and has a -1 charge, but a positron has no mass and a +1 charge. And so it's a really small particle with a positive charge. Now that positron will then escape, but it won't last long because it's just going to bump into some loose static electricity, which are just loose electrons hanging out in space. and it's going to turn into a photon of gamma radiation. And so positron production, because of its positron gets produced, finds an electron, and turns into gamma radiation, can be really dangerous for someone if they're exposed to it for too long. This little reaction down here talks about how a proton with one atomic number and a mass of 1 gets turned into a neutron with no atomic number and a positron. An example of this is a radioisotope of carbon with 11 as its mass number, which means it has 5 neutrons and 6 protons. So it's got an odd number of neutrons, which is typically unstable. And so what it does is then say, hey, carbon, why don't you take one of your protons and turn it to a neutron? So the mass is conserved, but the atomic number goes down by 1. And this is a more stable isotope. This is boron 11, and a positron is produced. Now, the final transformation that we're going to talk about is called an electron capture, and it accomplishes the same task as the positron emission, which we talked about in the last slide. But what happens is an unstable nucleus of, say, rubidium takes an electron from its electron cloud and just absorbs it into its nucleus, so it pulls it in. And when it does that, it takes one of the protons and turns it into a neutron. And so the atomic number goes down, so rubidium 37 protons turns to krypton with 36 protons, but the mass is conserved. Now this happens more likely and less dangerously than the positron emission because, as you remember, the positron emission then finds some static electricity and turns into gamma radiation. And of course, there's a little bit of electromagnetic radiation that is given off in this process, but not nearly the danger that I would expect from a positron emission. And so once again, everything is conserved. The atomic numbers are conserved. The mass is conserved in these sorts of transformations. The nucleus simply just takes an electron from its electron cloud, attaches it to a proton, and turns it into a neutron. So let's take a look at a couple of examples of test-like questions that you might have to encounter in a future quiz or test. Which element undergoes alpha decay to form lead-208? And so the things we need to know is, first of all, it produces an alpha particle because it's alpha decay. So that's a helium nucleus. And the other thing is it produces lead, which has a mass of 208. Now the atomic number of lead is 82. And so if we have to make sure that the mass is conserved and the atomic numbers are conserved in this alpha decay, then we just simply need to add the 2 plus the atomic number of lead, and we've got 84, and that element is polonium, and the mass then would be 208 plus 4, or 212. So the element that is in question is polonium-212. I gave you a couple of hints down here. The sum of the A values have to equal the same on both sides, and so does the Z values. So we need to basically backwards engineer. From the products, determine what the reactant was. Now the last one I want to talk about is this one, where I say, write the nuclear equation for thorium-231, which is the mass of the thorium, as it decays into protactinium-231. What type of decay is this? And so thorium has an atomic number of 90, and that's going to decay into protactinium, which has an atomic number of 91. And so I go from a low atomic number to a higher atomic number, and in order to do that, I must need to also produce an electron, and because an electron is produced, this is a beta decay or a beta emission sort of situation. Now, if you're still trying to pick up on how I did that so fast, remember the sum of the A values on either side of the arrow must be equal. And so the masses are equal to 231 plus 0. The same is true for the Z values. So if I go from 90 to 91, well, then I must have a -1 atomic number from the electron that will subtract from 91 to give me the 90. So the other thing to look at is the particle being emitted. That is a beta particle, so this is beta decay. We're going to finish off this first video with a little picture from the textbook. Basically, it has the 4 different types of emissions or decays that you will encounter. It's got a little nuclear equation that kind of helps you with that. But mostly I want you to pay close attention to what happens to the atomic number and what happens to the mass in each one of these 4 situations. Alpha decay is the only one that can change atomic number and mass. It drops 4 mass values because that alpha particle is 2 protons and 2 neutrons, and so we drop the atomic number quickly and we can drop mass very quickly. When it comes to beta emission, it actually increases the atomic number, but the mass remains unchanged. But the last two, the positron emission and the electron capture, accomplish the same thing. We decrease our atomic number and our mass remains unchanged. Well, hopefully you have a better understanding of unstable isotopes and how those nuclear transformations happen. Thanks for watching.